To our video here on alternating series. This is the first day of it. We're going to start talking about series that alternate. So what are examples of alternating series? Well, that's when we're going to have this -1 to the whatever power. That's going to mean it alternates based on if n is odd or even. So you can kind of see here, n is even, it's going to be positive on the, when n is odd here, my bad. N is odd here, all the even terms are positive, all the odd terms are negative, vice versa here. We just have -1 to the n. So just pay attention whether it's n plus 1 or to the n. And quick little side note here, if we ever have something like this, as we go to infinity, of -1 to the 2n, that's always positive. Because our power is always even, which is always be positive. And then the same type of conclusion can be made for this one right here. We have -1 to the 2n plus 1. That's always odd, so it will always be negative. It could be +1 or -1, does not matter. Okay, so let's talk about alternating series and how we can find it and all these fun stuff with this. So alternating series is just a series whose terms alternate positive and negative. If we know the limit, it doesn't really tell us much, going to 0, again, because of the nth term test. It goes to 0, it doesn't tell us anything. But it turns out that if the alternating series must converge if it has a limit of 0 and it decreases in magnitude. So essentially, the alternating series is we can use the nth term test for when it does equal 0, which is really nice. So we just call that the alternating series test. So let a sub n be greater than 0. Okay, so this would be the non-alternating part of the series. Okay, so like for this one, my a sub n would just be 1 over n. That's the non-alternating part. Okay, so it's one of these. Converges if the following two conditions are met. If the limit is equal to 0, and if this is decreasing in magnitude. Which means is that the absolute value of it is always getting smaller. So like for this one, if you ignore the signs to go from 1 to 1/2 to 1/3 to 1/4, that's decreasing in magnitude. Okay, and then actually, that's all I really got for you. So to use the alternating series test, you get to say these three things: alternates in signs, decreases in magnitude, and has a limit of 0. Okay, so also just take note of this. If it does not equal 0, then the series diverges. Does not say this diverges is not 0. This can only be used to prove convergence. Okay, so just be aware of that. So let's go through this first example right here. So first off, my a sub n term is everything that's not alternating. So that's the guy I'm going to be looking at here. So let's go ahead and go through this. So using the alternating series tests. So this is alternating because I got that -1. Okay, this is decreasing in magnitude, which means that it's going to get smaller. And again, that happens because my denominator is getting larger and larger every single time. So I can say that this is decreasing in magnitude. And now the limit part. Let's go ahead and find the limit. So the limit as n approaches infinity of just my a sub n term. And this is going to equal 1/2. So actually, I can't use the alternating series test because it does not have a limit of 0. So I went through all of that, and it actually turns out that we can't even use this test for this specific series. So this does diverge, though. So the series diverges, not by the alternating series test, by, in this case, the nth term test. All right. And just in case, real quick, for this decreasing in magnitude, let me go ahead and point that one out a little bit more. If you take the ratio of this, if you take the next term over the previous term, and then if this is less than 1, then it is decreasing in magnitude. So that's how you do know for this. So just can always plug it in to figure out if it's decreasing in magnitude. But again, for this series, it did not need the alternate series test. I just needed the nth term test. All right, so let's go ahead and talk about these guys right here. So I'm going to have a sub n to equal n over ln of 2n. Okay, so I'm just looking ahead, the limit here. I do know this one also does not equal 0. So this limit here of n over ln of 2n, n is growing faster. So since it's growing faster, on top, this is actually going to equal infinity. So this is going to diverge by the nth term test. All right, so these are two alternating series. But in this first two examples here, we're diverging by the nth term test, not the alternating series test. Don't worry, we'll do an example where we actually have to use the test here. So in letter C here, the non-alternating part is the 1 over n. I do know if I were to find the limit, I would get 0. So I can now state that it's alternating. This is decreasing in magnitude because every single term afterwards gets smaller and smaller. So it's decreasing in magnitude. And you have to say it's in magnitude because since it's alternating, it's not decreasing every single term, but in the absolute value of each term is decreasing. And then now the limit as n approaches infinity of 1 over n is indeed equal to 0 because it grows faster at the bottom. So now I can go ahead and say that the series converges. By the alternating series test. Okay. So if you notice, this is the harmonic series. A sub n is the harmonic series. So if it's not alternating, this would actually diverge. But since this is alternating, this one converges. So this is a alternating harmonic series. And you can kind of see right here what's going on. So we start from 0 and we jump up to a sub 1, drop back, and kind of see right here. We're getting closer and closer to that series sum right there. Okay. Last part is we're going to talk about absolute convergence or conditionally convergent. So a sub n is absolutely convergent if the absolute value converges. A sub n is conditionally convergent if this converges, but the absolute value diverges. Okay. So determine whether the given series converges or diverges. If it converges, determine whether it is absolutely convergent or conditionally convergent. So let's go through this. So first off, I have a sub n here is 1 over n to the 1/2. So this is going to be alternating. This is decreasing every single time, so it's decreasing in magnitude. And then the limit is 1 over n to the 1/2, which is 0. So this series does converge by the alternating series test. Okay. So now if I want to find out if it's absolutely convergent, I'm going to take the absolute value of this. So when I take the absolute value, do that in green. Of this right here, that's actually going to give me this guy right here, 1 over root n. Okay? And this would be a p series because p is equal to 1/2, which is which is less than 1. So this is going to diverge by the p-series test. Okay, so this would be a conditionally convergent series. So this only converges because it's alternating, so that's why it's conditionally convergent. If it wasn't alternating, then it would diverge. Actually, the same thing here would happen to C here. This is also conditionally convergent because I know that this is the harmonic series, which diverges, but since it's alternating, it doesn't. So this was another one that would be conditionally convergent. All right, and that's going to wrap it up for this lesson.